Let's get started. Good afternoon. Thanks for joining this session. My name is Adrian Huang from Lenovo. Today I'm going to talk about our recent works on enhancing scalability of the Vmalloc mechanism in the Linux kernel. It's a joint effort with Reski from Sony. He's the Vmalloc maintainer in the Linux kernel. Unfortunately, he's unable to join this session on site. Okay, agenda. I'll start a refresh on what the Vmalloc is, followed by how Vmalloc manages its address space, works through the legacy approach, and the enhancement we introduce using vmap node implementation. Finally, two remaining bottleneck issues we identified and resolved. Vmalloc page table population. As we know, Vmalloc provides the virtually contiguous virtual address backed by physically non-contiguous pages, which means that it requires the proper page table population, as shown here. PTE number 3 and 4 point to non-contiguous physical page, as shown here and here. This slide shows how Vmalloc tracks its address space by using the vmap area structures. Each vmap structure indicates the allocated and the unallocated one. And essentially, Vmalloc is a sparse allocation model. Note that each allocated vmap area structures includes a guide page, which helps detect the over-boundary access. It's quite helpful to detect the state overflow by leveraging the guide page by the Vmalloc mechanism. And this kernel config vmap state has to be enabled. Okay, so the next question is that how does Vmalloc manage the allocated vmap area space? Here comes two approaches. The first one is the legacy Vmalloc approach. The legacy approach has two different spaces. The first one is the free unallocated vmap area space. The second one is the allocated vmap area space. Each space has the pair with a repertoire and a linking list. A repertoire is used to find a corresponding entry efficiently, whereas a linking list provides a constant access to the previous or the next element. When accessing the shared data in each space, it requires the corresponding spin lock, as shown here, vmap area lock and the free vmap area lock. When a new allocation is made using Vmalloc, the kernel scans the free vmap area repertoire to find a suitable range. So it requires acquiring the spin lock, this one, free vmap area lock for data serialization. After a region is reserved, it's inserted into vmap area repertoire, and it requires grabbing the second spin lock, as shown here, vmap area lock. So for a single Vmalloc code, it requires both of global locks for data serialization. The legacy approach works fine on small system or underlying workload. But on a system with many CPU, the lock contention becomes a massive bottleneck. Okay, so imagine a situation where hundreds of threads are calling Vmalloc and vfree concurrently. Each of them must wait for each other. When the number of the CPU grows, the bottleneck dominates the execution time. So the workload throughput degrades significantly. Okay, so this motivates the redesign using the vmap node implementation, which I will get to the next. But it's important to remember here is that the legacy approach was simple, but inherently not scalable on modern multi-core systems. That's why we introduced the enhancement using vmap node implementation. Okay, so the concept of this enhancement is to decentralize the management of the allocated vmap area space by splitting them into vmap node structures. As you can see, it started from node number 0 to node number n, and each node structure has a separate repository, a linking list, and a lock. Rather than relying on a global lock to guide all Vmalloc allocation, the enhancement uses the multiple locks, one per node, to mitigate the lock contention. Okay, so by distributing the responsibility across nodes, this achieves the fine-grained locking, which means that CPUs working on different nodes do not block each other. Okay, so in a short summary, the legacy approach uses a co-locking. Legacy approach uses a global lock for the co-locking, which is the coarse-grained locking method. In contrast, the enhancement vmap node uses multiple locks for data locking, offering finer granularity. So this reduces the lock contention greatly. I will show the data later. So let's get more detail about the enhancement. There are 3 key design principles. VA allocation distribution. VA stands for vmap area, locality aware caching, and the scalability. For VA allocation distribution, the allocated VAs are across nodes. And you may wonder, how do we find the corresponding node? The answer is a hash function with the starting address of the VA object is used to identify the corresponding node. For locality-aware caching, once a node is identified, the associated VA object can be retrieved from this cache pool. And this cache pool manages the recently freed objects for reuse. For scalability, the number of nodes generally matches to the number of the CPUs in a system. However, it is kept to an upper limit of 128. And this slide shows how the Vmalloc works. Each node structures manage cache pool, like I mentioned earlier, and think of this pool as a fast-paced allocation. So if there are available entries in this cache pool, the allocator returns the request immediately. No need for expensive tree traversal and global lock acquisition. But the cache pool cannot meet the requirement. The allocator goes back to the fallback path as shown in steps 3, 4, and 5. Okay. And this slide shows the detailed information about per vmap node cache. And the show name is cache pool. And the cache pool aims to accelerate the frequent allocation of the same size. And the cache pool is essentially a list array to cache VA objects for the page size ranging from 1 to 256. Okay, so please note that the index 0 corresponds to 1 page VA, and index 1 corresponds to 2 page VA, and so on. Okay, so we are lucky. So if we are lucky in step 1, the allocation can get the VA objects from the cache pool. If not, The allocation gets the VA objects from the global vmap area space, which is the 4-byte allocation. This slide shows how V3 works. Okay, when the memory is free using V3, the VA object in the busy list is moved from the busy list to the lazy list. Okay, so and next, when the number of the pending lazy pages is greater than a predefined threshold, a background task is activated to move the VA objects in the lazy pages to the purge page. Okay, as shown in step 3, 4, and 5. Okay, and in step 4, a small fraction of the cache pool is returned back to the global free vmap area space. Okay. Finally, in step 6, VA objects in the purge list are moved to the cache pool. So as a result, the upcoming Vmalloc request can get the VA objects from this cache pool. Okay. And this slide shows how to find a corresponding node based on the starting address of VA objects as shown here. And there are 3 steps. But I would like to have more detailed discussion about the sub-parameters. For example, for this one, in this example is a 3 CPU system. So the parameter number vmap node is 3. For this parameter, vmap zone size 20, it means that how many pages or how many bytes for each node. Okay, but for better understanding, let's assume the unit is page. So 20 means that each node can span 20 pages. And next, the next node can span another 20 pages. For example, node number 0 can span 20 pages, starting from the page number 0 to 19. And for node number 1, as shown here, it spans 20 pages, starting from page 20 to 39. For node 2, it spans 20 pages, starting from page number 40 to 59. Okay, and next, the hash function is based on 3 parameters: address, the starting address of the VA object, vmap node size, and number vmap nodes. Applying this hash function gets the node number 1. So we place this VA object into node number 1, as shown here. Okay. Performance comparison. Okay, and it was conducted on a 32-core processor, along with the Vmalloc test module. And the lock contention was reduced from 93% to 16%, representing a 5-time improvement. In terms of throughput, a 12-time improvement was observed comparing to the legacy approach. So this shows that the enhancement can reduce the lock contention greatly. Okay. Next, 2 remaining bottleneck issues. After the enhancement, 2 issues were still visible on large systems. The first one is the purging inefficiency. The second one is the slow TLB flush with the KSN-enabled kernel. And first, let's discuss the purge inefficiency. This example shows soft lockup issues appear when running the Vmalloc test module on a 448-core system. Based on the code pace, as shown here, something on the purge pace was blocking the progress, as shown here. It spent too much time moving VA objects in the purge list to the cache pool. So next, let's break down what's going on. And each core has its purge list waiting for moving them to the cache pool, like I mentioned earlier. And every time we purge a single VA object in the purge list, the core, the CPU, has to execute the atomic subtraction instructions on this global counter. And the global counter, the name is vmap, lazy number. This global counter tracks how many pages are lazily held across all nodes. Okay. So when we purge the first VA object in this list, this global counter becomes 25. Okay. And each core iterates its purge list and executes the atomic instruction. Finally, this global variable, global counter, becomes 0. But the number of atomic instructions depends on how long the list is, meaning that each CPU has to serialize the access to the same memory location. Okay, so multiply this by thousands or even 10,000s of VA objects in the purge list, and hundreds of cores to run concurrently, you will get the extreme contention. Why? Let's see the root cause. Because instruction with the lock prefix might cost 100 clock cycles. So that might be a time-consuming task if we traverse and execute the atomic instruction in a long list. Okay, so here's a quotation from a public PDF file. The name is instruction table. It mentioned that a lock prefix typically costs more than 100 clock cycles, even on a single processor systems. So let's check the profiling data. The profiling data on a 448 core server shows that the average execution time is about 2 seconds, as shown here and here. However, the worst execution time is between 16 to 33 seconds. So that's why we saw a soft lockup issue appear and complained by the Linux kernel. Okay, solution. Our solution is to change the purge flow by using the local variables for counting, which means that every time we purge VA objects in this long list, we just accumulate the number of the purge pages or the number of the purge pages to its local variable. Okay, so this can avoid the atomic instructions for each single VA object in the purge list. So when we purge the first VA objects, we just accumulate the number of the purge page 5 for this VA object to the local variable 5. And when we purge the second entry, the number of purge page is 2. So the local variable becomes 7. After we purge all elements, this local variable becomes 30. Finally, a single atomic subtraction instruction is done to update this global counter. Okay, so this achieves 1 lock operation per code instead of 1 per VA object in the purge list. Okay, let's check the real-world impact. The performance gain was substantial on 3 tested servers, representing 99% improvement on a 72-core server, 1 92-core server, and a 448 core server. So this demonstrates that improvement benefits not just on large-scale machines, but also small systems. And this fix is upstream, and the information is shown here. And the second one is the slow TLB flash with the KSEN-enabled kernel. Again, this example shows a software lockup when we run the make command to compile the kernel source on a 255-core system. Based on the code path, it shows that when purging the Vmalloc address, the KSEN, as shown here, KSEN was busy on the TLB operation for the Vmalloc shadow memory triggered by KSEN. So, as shown here, KSEN spends too much time running the TLB flash operation for the shadow memory, for the Vmalloc shadow memory. So let's break down what's happening behind the scenes. And when we, each time when we purge the VA objects in the list, it requires a TLB flash to invalidate the corresponding TLB entries for that Vmalloc address triggered by KSEN. Okay, so the local CPU has to send an IPI TLB flash to all remote CPUs. However, the local CPU must wait all acknowledgements from all remote CPU. So imagine that if your system has hundreds of cores, this operation might spend amount of time to finish. Okay. So the local CPU iteratively flash TLB operation based on each single VA object in the non-purge list. So let's check out the profiling data. By using the ftrace, we found that over 2,800 cores are for TLB flash triggered by KSEN. And each of them takes about 7.5 milliseconds to finish. Multiply this, it spends 21 seconds to finish the TLB flash operation. So again, this is why kernel complains about a software lockup issue. Okay, the solution. The solution is to combine all TLB flashes into just one single TLB flash. Okay, instead of flash each VA individually, we get the starting address of all vmap areas. So let's assume the starting address of this list is A. And then we collect the end address of all vmap areas. And let's assume the end address is B. Okay, so the final step is to flash the entire range, as shown here. Flash TLB range A to B, starting address and the end address of this list. Okay, here is the performance evaluation data. The number of IPI was reduced from thousands to just one. And the execution time was reduced from 20 seconds. This is the ftrace result, okay? So it was reduced from 23 seconds to 1 second, represent 96% improvement. Okay. And conclusion, we will introduce the vmap node implementation. And this enhancement significantly improved the scalability of the Vmalloc which mitigates the lock contention. And after the enhancement, we observe the two remaining bottlenecks, and we identify and resolve. And these two issues, the fix for these two issues are upstream, which makes the Vmalloc more robust, efficient, especially on large systems. Okay, that's all I have. Thank you. Any question? Yeah.
I'm just concerned about the opposite end of the spectrum. So for embedded devices for 1 or 2 cores, does Vmalloc fall back to the legacy behavior below a certain threshold?
No.
Hash for every.
No. In a neural kernel, I think the enhancement was upstream in 6. I forgot the exact version. I show here. Let me show here. Let me check here. I did. Wait a minute. Okay. If your kernel version is 6.8, it will use the legacy approach. But if your kernel is 6.9 or later, it will use the enhancement, which is the vmap node implementation. So it does not have the automatically to switch to legacy approach or the new enhancement approach. Yeah.
Is there a performance hit of any kind on like a very slow single core embedded CPU, maybe because of the hash function or just it does more operations to get the Vmalloc?
I don't think so, because the hash function is quite small. It does not cost a lot of CPU cycle to finish it. Yeah.
I have small clarification question. I assume if you have some multiple socket system, huge system, you have multiple Newman nodes, as minimum 2, maybe 3 or something, 3 socket system.
Yeah.
So I simply guessing what is the relation, how this vmap node corresponds to Newman node.
Can you?
Okay, so if we have multiple socket system,
Yes, in the Newman nodes.
we have several Newman nodes.
Yes.
So what's the relation between Newman node and vmap node?
Okay. Okay. The short answer is that there's no any relationship with the vmap node and the Newman node. Okay. The vmap node just abstraction to describe how many vmap nodes they can support in the Linux kernel. But it depends on which CPU. No matter the trigger CPU is maybe in the Newman node 0 or 1. But when some CPU trigger maybe request a Vmalloc request, okay, we will try to use the hash function to find a corresponding vmap node to place the V object in this vmap node. And so no matter which CPU in which Newman node, you will also get this V object from the same vmap node, which can achieve just like I mentioned, there's a locality aware caching. Yeah. Did I answer your question?
Yeah, it's answered, but I think there's something worry about that if in terms of like in the same vmap node,
Yes.
it addresses from different Newman nodes.
Yes.
Its latency could be different. So it's
Okay. Okay. If not, okay.
One question, you mentioned it's a limit of 128 nodes for the VA nodes. It's currently limited to 128.
Yeah.
And it's a hash function, which up to 128, I presume, is generally 1 node per core. So how does that overflow to 256? Would it be 1 VA node per core, except
there's no overflow issue because based on the hash function, we use the modulo to make it run down or run. Let me show you the hash function. Okay.
They didn't calculate through my mind, but I'm presuming if you have 256 cores, each VA node
will serve 2 cores. Yes. So you can see this hash function. There's a modulo. Let me check. There's a modulo to this one, 128. Yeah. Okay. Thank you for joining this session.